Hello, and thank you for joining us today. Welcome to our webinar entitled The Transcreener CD73 Assay, Leveraging Nucleotide Detection to Measure Adenosine. I'm Justin Brink, Director of Marketing here at Bellbrook Labs. I'd like to introduce to you our presenter, Meera Kumar, Senior Scientist at Bellbrook. Meera has an amazing array of experience from developing assays like this to our CGAS discovery program. She's very well versed in strategies for discovering, developing, and advancing small molecule inhibitors for enzyme targets. I'd like to note that Meera and I are working in separate locations, as many of you probably are, to help slow the spread of the coronavirus. I hope you are all staying safe during this unprecedented time. Thank you, and with that, here's Meera.
Thank you, Justin, and welcome to the webinar titled Leveraging Nucleotide Detection to Measure Adenosine. Today's webinar focuses on CD73 and ectonucleotidase, which is an emerging target for drug discovery, especially in the immuno-oncology area. My talk will be divided into two segments. The first one where I introduce the drug target, and the second half where I focus on the assay development method. So please feel free to type in your questions that appear in the dialog box that appears on the screen. We will address those questions at the end of this webinar. If you would like to get hold of us, please do send us an email at info@bellbrooklabs.com. Extracellular ATP is a danger signal that's released by dying and damaged cells, and it functions as an immunostimulatory signal that promotes inflammation. However, the extracellular adenosine acts as an immunosuppressive or immunoregulatory signal that modulates the function of several cellular components in the innate and the adaptive immune response. Consequently, the balance between the ATP and adenosine concentration is crucial in immune homeostasis. CD39 and CD73 are two ectonucleotidases that cooperate in the generation of extracellular adenosine from the extracellular ATP by ATP hydrolysis, thus tilting the balance towards immunosuppressive microenvironment. Extracellular adenosine can prevent activation, proliferation, cytokine production, and cytotoxicity in T cells through the stimulation of A2A receptor. However, recent evidence has shown that adenosine may also affect other processes in T cell biology. So, as you can see, these are important players in the immuno-oncology pathway. And Bellbrook Lab has an assay for detecting CD39. And if you're interested in that target, please refer to our website. CD73 is a GPI-anchored enzyme that hydrolyzes AMP into adenosine and inorganic phosphate. CD73 also exists as a soluble form upon shedding of the GPI anchor and has very similar activity to its membrane-bound form. From a structural point of view, CD73 is organized into three domains: the N-terminal domain, which contains the metal binding sites, and the C-terminal domain. And there is a short alpha helix that bridges the N and the C-terminal domains. Now, the CD73 homodimers exist in two conformations. One is the open conformation, and the other is the closed conformation. Hydrolysis of AMP requires that the enzyme cycles between the open and the closed conformational states. CD73 is overexpressed in a lot of cancers, and since the accumulation of adenosine signals immune suppression, inhibiting CD73 is an emerging drug target that has a lot of promise. Different pharma companies have different strategies and approaches to inhibit this target. Some of those are, of course, inhibiting it using monoclonal antibodies or siRNA and small molecule inhibitors that are specific towards CD73. Now that would attenuate the growth or the metastasis of the tumors, and hence it's a very, very promising drug target. So of course, all this points out to having a high throughput sensitive assay that could measure adenosine. Therefore, an assay becomes an extremely important tool to pursue these approaches or to develop a small molecule inhibitor for CD73. So that's where Bellbrook comes in, and our initial attempt was to develop an antibody directly against adenosine, and we did try that approach, and that strategy proved unsuccessful, and therefore we took a slightly different route to develop an assay to measure adenosine. What we did here is the Transcreener Adenosine assay is coupled with adenosine kinase, so it relies on adenosine kinase to convert the adenosine that's generated in the reaction into AMP, and ATP gets converted into ADP. Now we use our Transcreener ADP assay to measure the ADP that's produced in this reaction. So ADP is detected using the Transcreener ADP2 assay using a competitive fluorescent polarization immunoassay. It's a mix and read assay, meaning you just do your enzyme reaction and add the reagents and read the plate. The assay uses a far red fluorophore, Alexa 633, and it helps in minimizing compound interference due to organic compounds. Now this assay relies upon the use of monoclonal antibody against ADP that can detect very subtle changes. In this particular example, its ability to distinguish between ATP, the triphosphate, versus diphosphate and the monophosphate. A little bit additional information about the Transcreener ADP assay. The Transcreener ADP assay, for those who have already used this assay, you know it has been for more than a decade and has been validated by multiple pharma companies. The assay is available in 3 different formats: the fluorescent polarization, TR-FRET, and fluorescent intensity. And the principle is basically the same. As ADP is generated, it displaces the tracer out of the antibody, and this change in fluorescence can be measured in any of the 3 detection outputs. So whatever instrumentation that you have, you can pick one of those formats. And this method is very simple, has been HTS proven. You just run your enzyme reaction, add your detection reagents, and read the plate. So the first step in developing an assay for Transcreener or for CD73 is to establish the selectivity of the ADP2 antibody. Now, what this means is just titrating various nucleotides that's shown here and to determine their EC50 values. So selectivity for ADP, so we are comparing everything with respect to the selectivity for ADP with respect to ATP. It's about 450-fold. The selectivity for ADP with respect to AMP is around 6,000-fold, and the selectivity of ADP with respect to adenosine is about 30,000-fold. So what does that mean? It means that you can detect ADP in the presence of excess of ATP or AMP, making this assay sensitive at initial velocity conditions. So the buffer that we set to use for CD73 is just tris with magnesium chloride and calcium chloride as the cofactors, and a detergent, bridge, 0.01% of bridge. And bridge is just to reduce non-specific binding between the protein and the antibody. The pH is at 7.5, and AMP is a substrate between, anywhere between 1 to 10 micromolar. The format is very simple. You have 10 microliter of your enzyme reaction and 10 microliter of your detection component, and the total volume is 20 microliter in the final reaction. So in any assay development process, the first step is to determine your detection reagents. And in our case, the detection reagents are antibody, tracer, and the adenosine kinase enzyme. Now, the tracer in all the transcreener assays is always kept constant at 4 nanomolar. So there is no optimization required there. The other two components definitely needed to be optimized. And just to note, I'm just walking you through the steps that we took to develop this assay. You do not have to do any of this. This is just explaining how we arrived at whatever the concentrations that you would in fact see in the tech manual. So the first thing to do is to identify the optimal antibody concentration for the assay. And we typically do this by just titrating the antibody concentration shown in the x-axis in the buffer of your choice and determine the EC85 concentration. Now, EC85 concentration would somewhere fall in this area that you see where this curve starts sloping down. Now, EC85 is a very good compromise between sensitivity and maximal assay window. You can also determine, here I've shown that you can use GraphPad Prism to determine the EC85 by just inputting the F factor as 85. And that would give you the value of antibody to use. And if you do not have such a software, and if you can only determine EC50, that's fine, because you can use EC50 and the hill slope and substitute it in the equation and get your EC85 concentration if you choose to go that route. The optimal antibody concentration we chose was 15 microgram per ml in the detection mixture, but it would be 7.5 in the final 20 microliter reaction. So the next step was to qualify the adenosine kinase, the coupling enzyme that we have to use in detecting adenosine. So we evaluated ADK from 2 different vendors, and for reasons obvious from the graph 1, we chose to proceed with ADK from vendor 2, which looked much better. And then in the second graph that you see here, we wanted to determine what is the optimal concentration of ADK to use in our detection mixture. So here you see that we titrated adenosine kinase. The complete stands for where you have your adenosine plus the ATP. The blue graph is just no adenosine, and the yellow triangle represents no ATP. Excuse me. So the enzyme concentration that we chose was about 10 nanogram over here, 10 nanogram per microliter. And at this concentration, the contribution due to non-productive hydrolysis of ATP was really minimal. So we went ahead with 10 nanogram per microliter as the most optimal antibody or enzyme concentration under these conditions. So the next test that we had to do was to run a standard curve where we vary AMP and adenosine, basically just mimicking a CD73 reaction where we start decreasing AMP while increasing the adenosine concentration, maintaining the nucleotide adenine concentration to be constant. We then add our detection mixture, which contains the adenosine kinase at 10 nanogram per microliter. We have the tracer and the antibody, and the table shows the Z prime value, and we could get a Z prime of about 0.7 at 10% conversion. So this established the proof of concept that we were ready to move to study the target to see if we can test it out with CD73 at this point. So this graph here, the first graph, shows the titration of CD73. So we, with our assays, we use recombinant purified enzyme, and we obtained the CD73 enzyme from R&D Systems. Shown here is the catalog number for ordering purposes. And the red graph, the red trace, represents the CD73 titration in the presence of 10 micromolar AMP, and the blue curve or the blue trace represents in the absence of AMP. And we chose to go somewhere between 1 and 5 picomolar CD73, which falls in this area right here. the competitive binding assays, this is something I always mention. The competitive binding assays are by nature nonlinear. So you would get a sigmoidal response when you plot your raw data. So if you want to convert your raw data into adenosine, we need a standard curve that's run under exactly similar conditions. So in this case, 10 micromolar AMP adenosine standard curve, and we interpolate these unknown values to get the adenosine concentration for all those concentrations of CD73. So the last graph, the third graph here, shows that there's a linear correlation between the CD73 and adenosine formed. What it shows exactly is we are following the Michaelis-Menten parameters, and we are at initial velocity conditions, because you can see we started with 10 micromolar AMP and we are producing about 1 micromolar adenosine. So we are at around 10% conversion, even if we go as high as 8 picomolar. But we kind of, to keep the enzyme concentration minimal, we focused on areas between 1 and 5 picomolar of CD73. Also, I wanted to mention that any concentration that you pick also gave us about 100 MP shift. So not only did it obey Michaelis-Menten parameter, we also got a really good MP shift with that concentration that we picked. So at this point, I would like to mention that we have not yet identified a quenching reagent for CD73 that would just stop the target CD73 and not affect adenosine kinase. Because as you can understand, we'll have to use the quenching reagent at much higher concentrations, and that typically at that high concentrations started to affect adenosine kinase. So we are continuing to investigate this, but at this point, the assay is only available as a real-time assay, and we recommend using the 60-minute time point, and perhaps stagger your reaction if you're running more than 100 plates while doing high-throughput screening. And that totally depends upon the automation you use, so how fast your plates are read by your instrument and so on. But the graph here actually focuses on the raw data obtained over time, and you can see we recommend 60-minute time point, and you can see any concentration that gives between 2 and 8 picomolar CD73 when you linearly transform it using a standard curve definitely gives you less than 10%, 20% conversion, and yet follows the initial velocity conditions. So that's just another example showing the data in real time. Now, the real time actually offers a lot of advantages as well, because you can read your plate multiple times, and you can determine the rates of the reaction and other such parameters if you need to. So it is advantageous for several other purposes as well. And with this assay, you could definitely use it for determining other parameters like residence time, the K on K off rates. And for more information on that, you could reach out to us. We have application notes and other material for those kind of experiments. So adenosine kinase is an interesting enzyme in the sense that it could use different cofactors, not just ATP, even though it's a kinase. It could use GTP, deoxy-GTP, deoxy-ATP as cofactors. And we just wanted to make sure that we were right in choosing ATP, and we were not compromising, on any other parameters by not choosing other nucleotides. So this is just an experiment where we titrated CD73 and then used adenosine kinase in conjugation with either ATP or GTP or deoxy-GTP. And although all three nucleotides do look good, ATP did perform a tad bit better, and we did choose ATP over all the other nucleotides for stability reasons, because GTP and deoxy GTP are both a little bit unstable and break down easily, and also to, it made sense for cost reasons as well, for pricing reasons as well. So this slide here shows the Z prime. Z prime is the ultimate measure of an assay to establish that it is HTS amenable. It's one thing to show Z prime with standard curve, but the actual test is with the enzyme. And the graph here shows 5 picomolar CD73 with 16 reps tested with and without AMP. The other control was the absence of enzyme itself. So this has AMP, but no CD73 shown in the inverted triangle. Now, when we calculated Z prime in both these scenarios, we see a Z prime about 0.79, 0.8. And what that translates to is that we would be able to unambiguously identify hits while you're screening with just a cutoff of 3 standard deeps. So you can identify your hits without any ambiguity, basically. That's what it means. So the next experiment that we ran was to use a tool compound to run a dose response curve to determine the IC50 value. This compound PSB 12379 was obtained from Tokris Bioscience, and the reported IC50 is between 10 to 12 nanomolar, and we obtained 19, which is within twofold and agrees with the literature value, and this was obtained using our assay conditions. We next wanted to see how this assay in real time would perform in a pilot screen. So we screened a subset of Cambridge diversity library, 1600 compounds. We ran a pilot screen. This is the data from 60 minutes, and the hits were identified by the compounds that showed up above the 3 standard deeps cutoff. These hits are currently being confirmed, and you can see the screen statistics shown in the red box here. The Z prime was 0.81 and Z factor 0.62, and a hit rate of 0.85%. All the controls were included. For example, just adenosine itself at 2 different concentrations, just to show that we are within the 10% conversion here, and the controls in the absence of enzyme. So the next step in our assay development process was to make sure that we were using the appropriate concentration of substrate, in this case AMP here. So we titrated AMP as shown in this graph, and although it's not an exact KM determination assay, because in the y-axis we don't show velocities, we are showing delta MP, but it kind of gives you a good idea of what the KM would be. And the KM we determined, the parent KM is around 3 micromolar, and the reported KM is between 1 to 5 micromolar. So with that data, we decided to use 3 micromolar as our AMP concentration to move forward for commercializing this assay, sorry. So, so we repeated some of the key experiments when with this new concentration of AMP. One is the standard curve that's run at 3 micromolar AMP to adenosine, mimicking the enzyme enzyme reaction, CD73's reaction. We wanted to ensure that the assay still performed under all our stringent specs, and shown is a good-looking sigmoidal curve, and which is also supported by great-looking Z prime values. As you can see, at 10% conversion, we get a Z prime about 0.82 and a good lower limit of detection. So all that looked really good. The next graph shows, this slide shows the CD73 titration at 3 micromolar AMP. Now the data is displayed in 3 different plots here. The first plot is just a linear scale similar to a scattered plot. This plot is effective if you want to see the assay window and the non-specific activity in the absence of substrate. So that's purpose of this kind of plots that we sometimes use to just look at our data. The plot number 2 is the same data shown in log scale in the x-axis, and it gives a sigmoidal plot, and this is what we typically use in our tech manuals or publishing to report the EC50 or the IC50 values or hill slopes, etc. So you need to just convert it into log scale. The third representation is when using a standard curve to interpolate the unknown values and converting the nonlinear data from the sigmoidal curve into the linear form. Now, I do want to mention at this point that running a standard curve is therefore not mandatory. It would be helpful if you need to represent the data in terms of adenosine. If you're just doing routine assays, I would just suggest running some controls, maybe at 10% conversion, like we had shown with 1.6 micromolar adenosine or just 0.8 micromolar adenosine. You don't have to run the entire standard curve, but if you want to convert your data into product formed, and if you want to show the percent conversion and those kind of parameters, you will need to run a standard curve. So that brings me to the summary slide. We have shown today the process, the steps that we took to develop a high throughput screening assay to measure adenosine using the Transcreener assay. The assay shows more than 30,000-fold selectivity with respect to adenosine, more than 6,000-fold selectivity with respect to AMP, and 450-fold selectivity with ATP. Now that enables detection at initial velocity conditions. The assay can be tuned in between 1 and 10 micromolar AMP, and we have shown today examples of CD73 titrations at 10 and 3 micromolar AMP. We do recommend that you use 3 micromolar AMP, which is at its Km that's determined by this assay. The IC50 value that we obtained agrees with the published values, which is good. And the pilot screen statistics should have convinced you to test out this assay for your high throughput screening needs. The next slide shows the, I'm sorry, let me go back here. The next slide shows the different targets that have been validated using the Transcreener assays. If any of these drug targets interest you or your colleagues who are unable to join us today, please do not hesitate to reach out to either Justin or me, and we would be happy to provide additional information or even arrange a webinar exclusively for that particular target if that's of interest. So here is the ordering information for CD73 assay. The catalog number is over here. We currently provide 1K and a 10K assay format, but you could always reach out to us for pricing and custom for bulk or dispensing options at this email, info@wellproklabs.com for a quote or for any other information that you might have. With that, I thank you for your attention and can now take any questions that you have. Yeah.
Hi, Mira. This is Justin again. You showed determining the ADP antibody concentration for the assay. Is that something a new user will have to do as well?
No, absolutely not. Those were just the steps that we undertook to develop this assay. So a person who is going to run this assay will just need to titrate their CD73, because if your expressing the protein in your lab, it might have slightly different concentration. You cannot probably use 1 to 5 picomolar without doing that. So you will titrate your enzyme concentration and add the detection components, which has already been predetermined for you. So the antibody concentration would be 10 microgram per ml. The adenosine kinase is 4 nanogram per microliter, and the tracer is always kept constant at 4 nanomolar. So all this information is in the tech manual. So it has already been predetermined for you. You do not need to run any additional experiments. You can directly proceed with enzyme titration, dose response curves, and or run screens.
Great. Here's another question. What is the suggested range of adenosine that the assay can detect?
Oh, that's a great question. So if you, I'm going to probably go back to, let me see if I can, if you remember, oh, I'm sorry, I'm going in the opposite direction. Give me 1 second here. I want to pull up the slide. Okay, this is the slide I want to pull up. So if you remember this slide, we add adenosine and we add adenosine kinase. Now this adenosine gets converted into AMP and the ATP gets dephosphorylated into ADP. Now this AMP goes back and into the pool of the CD73 reaction to keep the cycle going. So we can basically detect always be at initial velocity conditions, if you may, so anywhere between, we have shown today between 10 micromolar and 3 micromolar, but you could go even higher, and that should be fine with this assay.
And I think we have time for one more question. Are there any potential tips you have for running transcreener assays like this? Any common questions that come up from time to time?
Yes, I do actually. One is the buffer using nuclease-free water, because our assays depend upon detection of nucleotides, ADP over ATP, AMP, or any nucleotides basically. And so if you have any nuclease contaminants in your buffer, like even in the water, that can non-specifically hydrolyze your nucleotides. And hence we kind of always say use nuclease-free water with the assays, or milli-Q water should do very well too. And just make buffers fresh, don't use like a really old buffer, a couple months old, because that could easily be prone to contamination. That's one thing. The other thing that I have often been answering tech support questions is the kind of plates to use. So most of you probably are aware that for fluorescence assays you use black plates, and for TR-FRET you would use white plates. But there is a little bit more to it with transcreener assays. Our assays are not like ELISA assays. So we do not want high binding plates where the antibody comfortably sits down and coats the plate. We basically want it to be free floating, if you may, in the well, so it can capture the ADP or any nucleotide that's produced from the enzyme reaction. So we highly recommend using non-binding plates or at least low binding plates, because the medium and high binding plates could make the antibody coat the plate, and that would be a noise that you would see. The other thing is you have to pay attention to what volume. We give the users a lot of flexibility in running the assay that they, how they prefer. It's not some voodoo magic. We show it in, how to do it. So typically what we have been doing in our assays is 10 microliter of the enzyme reaction and 10 microliter of the detection mix. That's a 20 microliter reaction. So for those kind of low volume usage, we recommend using low volume plates, low volume 384 well plates. Now for so the standard 384 plates, for example, will not work because it has a total volume of about 80 microliters, and if you put 20 microliter in it, the instruments are not, the sensors would not go down as much, or it won't be sensitive enough to record the 20 microliter. So it's very, very important that you use low volume non-binding plates. Now if you are in one of those labs that do not like working with 384 well plates and would rather work with 96 well plates, we recommend using half area 96 well plates, and in that case run the reaction as 25 microliter of the enzyme reaction and 25 microliter of the detection mix. So 25 plus 25, 50 microliters in half area 96 well plate. Now that would reduce the reagent consumption and still give you the the flexibility of working with a 96 well plate. Now again, at Bellbrook, it has always been, users, customers come first. So we don't want to bind you to a format that just, that's the only way you could do it, like some other companies do. So even though we say 10 plus 10, if you want to increase the sensitivity of the reaction, you can run it as 15 plus 5. All you have to do is keep in mind that when you are doing it as 15 plus 5, the 5 microliter detection mix has to be at 4x concentration instead of 2x. So you always go back to your total final volume, which is 20 microliter, and decide, okay, is it 10 microliter or 5 microliter? So we give the users complete flexibility in fine tuning. We recommend that you use it as we propose, but there's always situations where customers have to fine tune the assay to suit exactly what they want to do and what they want to finally achieve.
Great. Thank you, Mira. I think that's all the time we have for today. With any other questions, please contact us via email at info@bellbrooklabs.com. Thank you for joining us. A copy of the webinar will be sent within the next 24 hours to review. Bye, everyone.
Thank you.